let's talk about monomial symmetric functions. So these are sort of the first example really, and a very important class of symmetric functions. Now we have already seen examples of these. Okay, so let's start by just giving the examples that we have seen. So recall when we talked about the following symmetric function with 6 terms, which was x1, x2, x3 with the variables. The powers were 3, 2, 1, and then all its symmetrizations. So you could think of it as keeping the variables fixed and then permuting the exponents in all 6 fashions. Okay, so I'll just write maybe one of them, 3, 1, 2, maybe another 3, 2, 1, say 2, 1, 3, etc. plus. Okay, so how does one think about what did we just do here? We started out with this basic monomial, any one monomial really, in this case x1, x2, x3 with powers 3, 2 and 1, and what we did is to sort of symmetrize it, add to this particular monomial all symmetrizations of that monomial. Okay, so that was one example. Now here's another one. You could take the powers say 4, 1, 1 plus all symmetrizations. Okay, now observe that, well, what are the symmetrizations here? I can put the 4 here, or I can put the 4 there. In this case, I don't get 6 terms like I did in the previous one. I only get 3 of them. Okay, so I started with this term and then symmetrized it. Okay, but of course in this case I only get 3 terms, and the reason I only get 3 rather than 6 is because, well, 2 of these numbers are the same. Okay, so I have 1 and 1, and because of that what I have are only 3 terms in the symmetrization. Okay, so these are both examples of what we will call monomial symmetric functions. So what's the basic definition? You start with a certain monomial. Now I could have started with any of these in the earlier case, for example, any one of the 6 monomials and then symmetrized, but it's sort of more convenient to start with maybe a specific monomial. So the convention that we use is the following, that we always say, okay, let's start with this monomial whose powers are decreasing. So I have 3, 2, 1. Okay, so among these 6 monomials, there's exactly one in which the powers are decreasing, right? Because the others, the powers are just obtained by permuting these numbers. And in the other case, well, decreasing may not always work. You might only have weakly decreasing. So 4, 1, 1 is a weakly decreasing sequence. Okay, so that's something that I pick. So let's give the general definition now. So given a multi-index, so let me just say definition. So let alpha be a multi-index. Define lambda of alpha. So sometimes denoted, sorry, let me give it 2 different notations. One is alpha in decreasing order, also denoted lambda of alpha. So these are both 2 different notations. So here's the definition. This is nothing but the sequence alpha 1 through alpha n arranged in descending order. Okay, so the sequence of alpha I going from 1 to n, but rearranged in descending order. The sequence alpha I arranged in weakly decreasing order. Okay, so that's just notation, lambda of alpha or alpha down arrow. Now, given an element like this in weakly decreasing order, so let lambda denote a multi-index, let lambda be a multi-index which is in weakly decreasing order. Okay, so it's at plus n, therefore of course all the lambda n's are positive, so I'm just reiterating that fact. Now given this, let's define. So here comes the main definition now. The monomial symmetric function or the monomial symmetric polynomial called m sub lambda, indexed by lambda, of x1, x2, xn, the variables. This is defined as follows. You take the monomial x to the lambda. Okay, it's exactly like in the earlier two examples that we talked about. You take this one single monomial x to the lambda, and then you symmetrize it in all possible ways. Plus, let me just write it informally for a start, plus all its symmetrizations. Okay, now what does that mean? Let's write it out a bit more formally. This is m lambda is defined to be the sum of all monomials x to the alpha, where, so how do you capture the statement that the multi-index alpha is a symmetrization of the multi-index lambda? Well, if you rewrite alpha in descending order, so that's, recall the notation we defined, lambda of alpha or alpha decreasing. So lambda of alpha should give you the original lambda that we fixed. Okay, so this is the definition if you wish. M lambda of x1, x2, xn is the sum of all monomials x to the alpha, where alpha ranges over alpha such that alpha ranging over multi-indices such that lambda of alpha is lambda. Okay, so this guy is called the monomial symmetric polynomial. Indexed by alpha, indexed by lambda. Okay, and of course the two examples that we already talked about. So what are they? So if you take sample, you take three variables, so I take n equals 3, and if I pick lambda to be 3, 2, 1, then that's the monomial symmetric function is going to be sum of those 6 terms that we have seen already, x1, x2, x3, 3, 2, 1, okay, plus x3 in some other order, 3, 1, 2, etc. Okay, so 6 terms total. So that's our usual, the example we have looked at previously. Now, second example, if we take lambda to be, so same thing, n equals 3, take lambda to be 4, 1, 1, it's in weakly decreasing order, then m lambda, the monomial symmetric function, has the starting monomial, which is 4, 1, 1, then all the other alphas such that when you arrange them in decreasing order, you get 4, 1, 1. Okay, what are those? Those are exactly 1, 4, 1 and 1, 1, 4. Okay, so that's the, those are the two examples that we already looked at. Okay, now some quick facts about these symmetric functions, which is very easy to see. So observe, fact, what's the degree of this monomial? So, well, I should say the monomial symmetric polynomial m lambda is well, its symmetric is clear, but more than that, all the terms which occur in it are of the same degree. So that's what you call a homogeneous symmetric polynomial, okay, with what's the degree of all the monomials which occur in it? Degree of m lambda is exactly, well, as we have just seen, the powers that go on top of the variables are just the lambda i's. Okay, and in every monomial you just get the same lambda i's, but maybe in some other order. Okay, but the total degree is just going to be the sum of all the lambda I. Okay, so that's a simple fact. Okay, good. So let's say a bit more about this. We just need some notation. So let me just introduce something which will come up again and again when talking about symmetric polynomials. This is what are called integer partitions. Okay, sometimes just called partitions if it's clear that we are dealing with integers. Okay, so what's a partition? Well, its definition, an integer partition or a partition is a decreasing sequence. Is well, what is it? It's a weakly decreasing sequence. It's something of the following kind. Pi is a weakly decreasing sequence, pi 1, pi 2, pi k, and we assume that they're all positive, so they're all natural numbers now. Okay, so what an integer partition is, well, in words it's nothing but a weakly decreasing sequence. So this is notation, is a weakly decreasing sequence of natural numbers. And this is usually how we write it. We call it pi, and then we write pi 1, pi 2, pi k. Okay, good. So here's some notations and simple properties. So, well, examples first. Example, for example, 4, 2, 1. Okay, this is, you can think of the tuple 4, 2, 1 as a partition, or you can look at, say, 2, 1, 1. That's also a partition, and so on. These are all examples of integer partitions. Now, we have some standard terminologies or notations here. We write, given a partition pi, we write mod pi to be the sum of all the pi i's. Okay, so I said there are k parts. Okay, so what is k here? K is as in my original definition here. So I wrote pi as pi 1, pi 2, pi k. So there are k natural numbers arranged in decreasing order. Mod pi is just a sum of all those natural numbers. Okay, and length of pi is the number of elements in the sequence. So it's that number k. Okay. Now we also tend to think of partitions when we write a partition as pi 1 greater than or equal to pi 2 and so on. But we often think of pi really as follows. So pi is thought of as really the sum. See, this is how we really think of an integer partition. It's pi 1 plus pi 2 plus pi k. So example, so what is this? So here's an example. Let's come back to this. So 4, 2, 1 that we wrote out already. We think of this as being the partition or the sum 4 plus 2 plus 1. Okay, and observe 4 plus 2 plus 1 is 7. So what is this 4, 2, 1 telling you? It's a way of splitting 7 into a sum of natural numbers. Okay, and we don't want to keep, we don't want to think of 4 plus 2 plus 1 as being different from 2 plus 4 plus 1 or 1 plus 4 plus 2 and so on. So we just want one single way of saying, okay, I have taken 7 and I have sort of split it into these three numbers, 4, 2 and 1. And so we just say, okay, let's just arrange it in decreasing order so that we don't keep counting the same thing, think of the same thing in different orders. Okay, so 4, 2, 1 is a partition of 7, and the individual elements pi 1, pi 2, pi k are sometimes called the parts of the partition. Okay, now So this is usually how we are thinking of a partition, as really being the sum. Okay. Now what else is important here? Well, let's give these things names. So here's some more notation. P of D, script P of D, is just the set of all partitions of D. Okay, this is the set of all integer partitions pi such that mod pi equals D. Okay, so we usually say these are all partitions of D. Okay, now that's one. Here's another piece of notation. If mod pi is D, if pi belongs to PD, we also write so many different notations to express the same thing. We say pi and put this symbol here to say pi is a partition of D. This is how we read that funny symbol in the middle. Okay, so this is another symbol, and we'll also need to bring in n somehow. Okay, n, remember, for what we have done so far, is the number of variables. So what is PDN? Okay, so here d and n are natural numbers. So let's say d and n are greater than or equal to 1. Right. Then what's PDN? Well, this is the set of all partitions of D such that the length is at most n. Okay, which means, recall, the length is just the number of parts, the number of natural numbers that occur in the sequence pi. Okay, now if you have an element in PDN, so if pi belongs to PDN, what does it mean? It means pi can be written as follows: pi 1, pi 2, pi k greater than or equal to 1, with k is a number of parts, right? That's the length. K is supposed to be at most n. That's the definition. Okay, so you have less than n non-zero numbers, pi 1, pi 2, pi k here, but in practice what we'll do is we'll often think of this. So I mean, here's one thing you can do. You can think of this as a sequence with exactly n numbers by appending some zeros at the end. Okay, so we can also do the following. We can append, well, how many zeros? N minus k zeros at the end. Okay, and think of pi as, well, as a sequence with n numbers, as pi 1, pi 2, well, pi k, and then we just put zeros for all the rest. Just define this to be 0, 0, 0. Okay, so now it's exactly an n tuple, of weakly decreasing numbers. Okay, now why are we doing all this? Well, because of course we are interested in talking about monomial symmetric functions, where these n tuples of weakly decreasing numbers are what you need to index the monomial symmetric function. Okay, good. So now why am I doing all this? Recall, well, maybe not recall, just say given a partition pi in PDN, okay, we append these n minus k zeros at the end. So what we'll do is to say, we think of it as an n tuple as above, okay, as we just described by appending some zeros. And once you do that, you can use that pi to index. So let's call this, instead of pi, let's maybe call it lambda, to be consistent with the lambdas that we've been using throughout. So given an n tuple lambda, given a partition lambda, of D with at most n parts. We append n minus k zeros and make it into exactly n numbers which are weakly decreasing. Then define, then look at, then consider the monomial symmetric, the corresponding monomial symmetric function. Okay, so this is what we're going to do. We're going to take all such partitions in PDN and look at the corresponding m lambdas. And here's the key theorem. It's maybe the first important theorem that we will encounter in this business, which is that these monomial symmetric functions, the m lambda x1, x2, xn, when lambda varies over the partitions of D with at most n non-zero parts, this set, and the meaning is what we have said above, you have to append zeros to make it exactly an n-tuple. This collection of monomial symmetric functions is in fact, it's a basis. Okay, but remember we were talking about, everything was over Z. We were talking about polynomials with coefficients in Z. So this is a Z basis, okay, of the space of homogeneous symmetric polynomials. Of degree D in n variables. In n variables x1, x2, x. Okay, now so I mean if instead of Z we were talking about polynomials over, let's say, the rational numbers or the complex numbers or other fields, then this space would be a vector space, and what we are constructing, what we are claiming here is that m lambda would actually be a basis of that vector space. Okay, now here we are working over the ring Z, so maybe the correct way of saying it is it's a module over Z, and that this forms a basis over that ring R. Okay, now without really getting into too much of the technicalities of modules and so on, what we really need to prove in order to establish this theorem is sort of what the word basis usually means, which is that it is every element of every polynomial, homogeneous symmetric polynomial of degree D in the variables x1, x2, xn, we need to show it can be written as a Z linear combination of these m lambdas. And secondly, that so that's the spanning condition, and the linear independence condition says that if some linear combination of the m lambdas gives you 0, then the individual coefficients in that linear combination have all got to be 0. Okay, the usual two properties. So let's prove the first one, the spanning property. So let's take a polynomial, let f of x1, x2, xn be a homogeneous symmetric polynomial of degree t. Okay, and what's the standard way of representing a polynomial? It's a sum of monomials, be a homogeneous symmetric polynomial of degree t. Okay, now what does homogeneous symmetric mean? It just means that every monomial has the same degree. So what this means is that so what we have is the following. So if you take so let's call this the support of this polynomial, it's just those alphas. So just take the collection of alphas for which this coefficient is not 0. Okay, now just take those monomials which actually appear. That's what this means. So letting support denote this, we conclude that for every alpha in the support, the degree is d of that corresponding monomial, right? So that just means the sum of the alpha i's must be d for all alpha in the support of F. Okay, so that's just homogeneous of degree d. That's all it's saying. Okay, now let's see how do you express this finally as a linear combination of monomial symmetric functions. Well, from each of these monomials whose total degree is d, sum is d, we just pick out the ones which are in decreasing order, okay, as we saw earlier. So let's call that set something. Let's S denote the set alpha in support of F, those alphas which appear, such that alpha is in decreasing order, alpha is weakly decreasing. Okay, and observe, this is nothing but another way of saying this is support of F intersection the set PDN. Okay, so PDN, recall, is just what? All numbers, weakly decreasing numbers of length n with total sum equals d. Okay, so that's how we view partitions of as we said, the identification PDN is all those partitions with length at most n, but we think of them as having length exactly n by appending some zeros at the end. So this is exactly this set. Now the claim is that the fact that F is symmetric tells you something. It says that it's actually enough to just focus your attention on these monomials whose exponents are in decreasing order, because that will tell you what the coefficients of all the other monomials are, okay, because those are just obtained by permuting these indices. Okay, so observe F is symmetric. If it's a symmetric polynomial, says that C alpha, the coefficient C alpha, will be the same as the coefficient of the monomial C of lambda of alpha. Okay, lambda alpha is the alpha arranged in decreasing order. Okay, this is for all alpha. So what does it mean? This just means that for the polynomial F can just be written as follows. Instead of summing over all the, see earlier it was actually a sum over all alphas in the support of F, C alpha, X alpha, that was the original expression. But now what we are saying is you just focus on those alphas which are in decreasing order. Okay, so I'll just focus on those, instead of alpha I'll call it lambdas which are in support of F intersection PDN, the ones which are in decreasing order. So that was what we called the set S. Now for this fixed lambda, what this property here says, is that the constant C alpha is the same as the constant C lambda of alpha. So I can pull out that C lambda term constant from all the terms, and now this is just going to be sum X alpha, where alpha is going to range over those elements of the support such that if you arrange it in decreasing order, it gives you this particular lambda. Okay, and now that's exactly what we want. That's the monomial symmetric function by definition. So this is C lambda M lambda. Okay, so this establishes the first part, that any homogeneous symmetric polynomial of degree d can be written as a linear combination of the m lambdas, lambda coming from, well, in this case lambda came from S, and S, remember, is a subset of PDN. Okay, so you can write, so S by definition is a PDN intersection the support of F. So you can write the given F as a linear combination of the m lambdas, where lambda varies over PDN. Yeah, that's the first thing. Now second statement we want to prove is that the linear independence statement. So what does, in some sense, linear independence now require? It says that if a certain linear combination is 0, okay, lambda ranging over PDN, then each of those C lambdas must be 0. Okay. Now observe that, well, if you just stare hard at this left hand side, you will observe the following fact, that the monomial, look at this particular special monomial, x to the lambda. Okay, so you fix a lambda, so fix, maybe we should call it something else, fix mu maybe in PDN, take a particular element and look at the coefficient of that particular monomial x to the mu. Okay. Now what's the, when does it, how can it possibly appear on this left hand side? The monomial x to the mu occurs on the LHS only in the term m mu of x1, x2, xn. Okay, there's no other way you can get the term, the monomial x power mu. Okay, mu is already in decreasing order. For it to occur on the left hand side, it must occur inside at least one of the m lambdas. Now if x to the mu occurs inside some m lambda, if you just think about it for a minute, you will realize lambda has to be mu, right? If lambda is different from mu, then that term x to the lambda is going to be the one which has decreasing powers. So for it to be x mu, lambda and mu had better be equal. So the monomial x mu occurs on the LHS in exactly one term, that's the term m mu. Therefore, what's its coefficient? Therefore, its coefficient on the left hand side is just the term c mu. Okay, but the term x mu occurs on the right hand side with coefficient 0. Okay, therefore c mu had better be 0. So that's the conclusion. Therefore c mu is therefore equal to 0. Okay, so that concludes the proof. So we are done.